Hello. You have perhaps guessed what the last issue that we need to cover this week is, but just in case you haven't, let's introduce Alice and Bob one final time to make clear what we are doing. This time, Alice and Bob have estimated a probability density function for a random variable. Alice has got the result shown here, and Bob has got the result shown here. As always with these two characters, they have not characterized the distribution for the random variables they have sampled in their experiments. It is thus not possible to say whether Bob has reproduced Alice's result or not. This video is thus going to explain how we can illustrate the randomness in the sampled results when we generate these estimates of the probability density function. The beginnings of a Python code for doing this is shown on this slide. As you can see, this code is very similar to the code that we used when we were estimating the probability mass function for a discrete random variable. The key differences are illustrated in bold. Furthermore, the reason there are differences are primarily because of the way we have to regularize when we estimate the probability density function by repeatedly sampling the distribution. This was discussed in my video on calculating estimates of the probability density function. As we did when we wrote this resampling code for the discrete random variables, we have encapsulated all the code that we have for generating our individual estimates of the probability density function into a function called genhistogram. This function takes two arguments: n samples, the number of samples that you want to generate to compute your estimate of the histogram, and n bins, the number of bins to use for the histogram. Within the genhistogram function, we calculate the variable del x, which tells us the width of the bins. In this code, I am generating uniform random variables between 0 and 1, and thus del x is just 1 over the number of bins. If you were sampling some continuous random variable that could fall between a and b, del x would be b minus a all over n bins. The code then generates the n samples random variables and determines which of the bins each of these random variables falls within. We can thus keep track of the number of times the result falls within each bin of the histogram using the numpy array called histo. Once all our samples are generated, the estimate of the histogram that is stored in histo is normalized by dividing by the number of samples multiplied by the width of the bin. When this array is returned from the function, it thus contains a series of estimates of the probability density function for the random variable. We can generate multiple samples of this estimate of the probability density function using the code shown here. This code is exactly the same as the code that we used when we generated multiple samples of the estimate of the probability mass function when we were considering discrete random variables. Because we have multiple samples for the value of the probability density at each of the bin midpoints, we can use all the tools we have learned about for displaying the various features of the distribution. For example, we can calculate and plot the medians of each of our various estimates by using the commands shown here. We could use PLT error bar as we did for the discrete random variable to draw an error bar around each of the points at which we have estimated the probability density function here. As we are trying to estimate a probability density function, however, my preference is to display the range of possible curves using a colored region. The way you do this using matplotlib is shown here. The fill between command here colors the region between the line that passes through the points xvals lower and the line that passes through the points xvals upper. The final result of this code thus looks something like this. In terms of reproducibility, this diagram tells other researchers that 90% of all our estimates of the probability density function have fell within the blue region. There is thus a 90% chance that any estimate they generate from the same distribution will fall within that region. I hope that is reasonably clear. Try to complete the exercises that follow, which will give you an opportunity to apply this method yourself. There will then be lots more opportunities to apply this technique to more complicated continuous distributions in the weeks that follow. Thanks for your attention and good luck.